This is part 1 of lecture 5.4, Countable Sets. In this video, we will give some sufficient conditions in order for a set to be countable. The results that we will present are generalizations of results that we have learned for finite sets. At the end of this video, you are expected to be able to use these properties to give short proofs of statements involving countable and uncountable sets. We learned in lecture 5.3 that a set is countable if and only if it satisfies one of the following properties. It is finite, or it is numerically equivalent to the set of natural numbers. Our first result is a generalization of a similar result for finite sets, given countable sets A and B. If A is countable and B is numerically equivalent to A, then B is countable. That is, every set which is numerically equivalent to a countable set is itself countable. If A is countable and B is a subset of A, then B is countable. That is, every subset of a countable set is countable. The proof of statement 1 is left as an exercise. Note that the argument is very similar to the one used for the case of finite sets, which is to be found in lecture 5.2, part 1. You need to consider two cases, namely, the case where A is finite and the case where A is infinite. For the proof of statement 2, we have two cases, namely, either B is finite or B is infinite. If B is finite, then B is countable and we are done. For the case where B is infinite, we will use the following property of the set of natural numbers, which is known as the well-ordering principle. This states that every non-empty subset of natural numbers must contain a smallest element. Continuing with the proof, assume that B is infinite. Since B is a subset of A, it follows that A is infinite. Since A is countable, A must be numerically equivalent to the set of natural numbers, and so there exists a bijection F from A to N. Since F is 1-to-1, it follows from exercise 6 in lecture 5.1 that the image of the set B is numerically equivalent to B. And since B is infinite, it follows that f of B is infinite. In particular, f of B is a non-empty subset of N. Therefore, by the well-ordering principle, f of B has a smallest element. For this proof, assume that the set of natural numbers is the set of positive integers. Define the map G from N to F of B by induction as follows. Set G of 1 to be the smallest element of f of B. Let n be an integer greater than or equal to 2, and suppose that the set of images of the numbers 1 to n minus 1 is finite. Since f of B is infinite, f of B is not equal to the set of images of the numbers 1 to n minus 1. It follows that f of B minus the set of images of the numbers 1 to n minus 1 is a non-empty subset of the set of natural numbers. Hence, by the well-ordering principle, this set also has a smallest element. This is true for all integers greater than or equal to 2. And for such n, set G of n to be the smallest element in the set f of B minus the set of images of the numbers from 1 to n minus 1. We are going to show that the function g is a bijection. To show that g is 1-to-1, let m and n be natural numbers, and assume that m is not equal to n. We will show that g of m is not equal to g of n. Without loss of generality, suppose that m is less than n. Then m is one of the natural numbers from 1 to n minus 1, so that the image g of m belongs in the set of images of the numbers from 1 to n minus 1. On the other hand, it follows from the definition of the map G that g of n is greater than g of k for any number k from 1 to n minus 1. So g of n does not belong in the set of images of the numbers from 1 to n minus 1. Thus, g of m is not equal to g of n. Therefore, the function g is 1-to-1. Now we show that g is onto f of capital B. Let C be an arbitrary element of f of B, and let capital Y be the set of all elements small y in f of B such that y is less than C. We have two possibilities. Either C is equal to 1 or C is not equal to 1. If C is equal to 1, then the set capital Y is empty. And if C is not equal to 1, then C must be greater than 1, and the set capital Y is a subset of the set of numbers from 1 to C minus 1. In either case, the set capital Y is finite. Hence, the set capital Y has cardinality n for some non-negative integer n, and C is the smallest number in the set f of capital B, which does not belong to the set Y. Thus, C must be the image under the function g of the number n plus 1. Since n is non-negative, n plus 1 is positive, and thus n plus 1 is a natural number. This shows that the function g is onto f of capital B. Therefore, the function g is a bijection from the set of natural numbers to f of B. Hence, f of B is numerically equivalent to n. It follows from the transitivity of numerical equivalence that B is numerically equivalent to n. So the set B is countable, which completes the proof of statement 2. We will use the previous result to show that the set of all positive rational numbers is countably infinite. Recall that the set of positive rational numbers is equal to the set of all quotients of natural numbers. Note that here we assume that the natural numbers are the positive integers. We need to show that the set Q plus is infinite and countable. Since the set of natural numbers is a subset of Q plus, and since the set of natural numbers is infinite, it follows that Q plus is infinite. Let D be the set of all ordered pairs PQ of natural numbers P and Q, such that P and Q are coprime. Then D is a subset of the Cartesian product n squared, where the set n squared is countable. Recall that by the previous theorem, any subset of a countable set is countable. So the set D is countable. Define the function f from n to q plus by setting the image of the ordered pair PQ to be the fraction P over Q. It is left as an exercise to show that f is a bijection. When this is done, it follows that D is numerically equivalent to Q plus. By the previous theorem, a set which is numerically equivalent to a countable set is countable. Therefore, Q plus is countable. Hence, Q plus is both infinite and countable, and thus, Q plus is countably infinite. The following is a consequence of the previous theorem. A set is countable if and only if it is numerically equivalent to a subset of the set of natural numbers. To prove, assume first that the set S is countable. Then either S is empty, or for some positive integer k, S is numerically equivalent to the set of integers from 1 to k, or S is numerically equivalent to the set of natural numbers. Clearly, the empty set, the set of integers from 1 to k, and the set of natural numbers are all subsets of the set of natural numbers. So in each case, S is numerically equivalent to a subset of n. Conversely, assume that S is numerically equivalent to some subset T of n. Since n is countable, it follows from the previous theorem that t is countable. Since s is numerically equivalent to t, it follows also from the previous theorem that s is countable. This completes the proof of the corollary. You have come to the end of part 1 of lecture 5.4. Before you proceed to part 2, you are strongly encouraged to do the exercises given at the end of this video. Thank you for your attention.